Today's video is all about launch velocities, and we're going to examine with this video how much velocity is going to be required for our launch vehicle to deliver a specific payload into a particular orbit. We have three objectives. Our first is to understand the four phases of our launch vehicle ascent. The next is to be able to understand what the topocentric horizon or SEZ coordinate frame is. And we're going to use that coordinate frame to calculate our delta V design, which is our last little objective. So let's look at our ascent phases to begin with. So to begin with, we're going to have four different ascent phases, and our first ascent phases for our launch vehicle is going to be that of vertical ascent. So here our launch vehicle is going to start out on the launch pad and it's going to try to gain as much altitude as possible. It's also moving through the densest part of the atmosphere, so it's going to try to do this as quickly as possible because the dense atmosphere is going to incur the most drag on our spacecraft or on our launch vehicle. The next is called the pitch over portion of our launch vehicle ascent. The pitch over is where we start to initiate this horizontal piece. So it's not enough for our satellite to be in orbit at a particular altitude. In order to really truly be in orbit, it has to have a distance above the Earth and a horizontal velocity. So here we're starting to incur some of that horizontal or downrange velocity. The next is the third phase here is our gravity turn phase. So here we're allowing Earth's gravity to pitch us over even more so we can apply even more acceleration so that we can achieve the velocity that we need to be in orbit. And lastly, we have our fourth phase, which is called the vacuum phase, where we're above Earth's atmosphere and we can truly start to accelerate even more to achieve that velocity that we will require to be in orbit. So these are our four phases, and we're going to use the fact that we're going to be in these phases in the subsequent slides, and we'll calculate exactly how much velocity we're going to require to move through these phases. So before we do that, we should probably introduce a new coordinate system that's going to make our delta V design calculations a little bit easier, and that is the topocentric horizon frame. So to begin with, a topocentric horizon frame is going to have a point of origin at our launch site, which is kind of this topocentric, meaning surface-centric. That's going to be our origin point. So that's where we're going to start. In this case, I'm showing you a picture of the Kennedy Space Center, so out here in Florida, and here we've got our origin point on the surface of the Earth. The next is going to be essentially our fundamental plane, and that's going to be that of the local horizon. So our local horizon is going to be defined as the south and east by the south and east vectors that are leading from our launch site. So if we're standing at our launch site, in this case would be Kennedy Space Center, we're looking directly due south. That would be the vector that points along our principal direction. And then if you look due east, that's going to be the east vector. And then lastly, we've got this z vector, which points up out of the plane. So it's going to point from the launch site up into space, directly overhead. That's going to be the zenith vector. So this is the SEZ, or topocentric horizon coordinate frame. We're going to use this to calculate our delta V design. So let's do that now. So how do we go about calculating delta V design? So if I were you, I would pull out your equation sheet and start looking at these equations as I start going through this. But essentially, as you look at your equation sheet, we know that our delta V design is related to delta V needed plus V losses other than gravity. So what do these terms mean? So our delta V design is the velocity the rocket must deliver to reach the desired orbit. Great. So that's how much delta V we need to incorporate into our design. The next is our delta V needed. So this is going to be the velocity needed to get from the launch site to the orbit. But there's this other term, V losses, and that is because we're actually moving through the atmosphere, and so we're going to have drag and steering and back pressure losses and all sorts of other losses that are going to need to be taken into account for our design. So it's not enough to just design our rocket just to go from the surface of the Earth up to our orbit. We also have to incorporate what these losses are. So these are the losses that we'll describe to you, and typically these values, V losses other than gravity, is a number that we will give you when you're actually working these problems. So what is delta V needed? Well, delta V needed actually has several different components in and of itself, and we're going to talk about what each of these things are in more detail, but I'm kind of showing you here as an overview as to what these three things are. So the first one is VBO. So VBO is the velocity needed at rocket burnout, so BO stands for burnout, to be in the desired orbit. So this is going to be the velocity that we're going to be required to have in order to be in that particular orbit. The next is going to be our launch site velocity. So our launch pad is going to be fixed on a rotating Earth. So that's going to be useful to us because that velocity is going to be part of the velocity that we don't have to burn or don't need because that's already going to be given to us because it's on a rotating Earth. So yay there. And then lastly, we have this V loss gravity. So this is the velocity needed to overcome the gravity to reach the correct altitude. So we'll talk about what each of these are now. Let's start with VBO. So VBO is a velocity that you've actually calculated starting in block 1. VBO in this block is the velocity that we need depending on whether we're in a circular or an elliptical orbit. And we know the velocity for a circular or elliptical orbit is just simply a relationship with this equation. So V equals the square root of 2 times the quantity mu over r plus epsilon. Or if you're in a circular orbit, it's a little bit simpler. However, we need to express this velocity not just in terms of just a magnitude. We actually need to express it in our coordinate system. So to do that, you can use your equation on your equation sheet here. And that says that the vector VBO expressed in the SEZ frame is related to its magnitude, VBO. So if VBO does not have the vector symbol over it, it's just a magnitude, times the cosine of phi times the cosine of beta, and then we've got another phi and a beta here, and then we've got a phi. So what are these two angles? Well, our beta is our launch azimuth, and our phi is our flight path angle. So the launch azimuth, as you might remember, is simply this angle here that we calculated from the launch windows lesson. So that would be your launch azimuth. So that's the direction we're going to be launching. And our flight path angle is actually something that we will either give you or you might be able to calculate it if you know that you're actually inserting into apogee, perigee, or circle, because if that's the case, your flight path angle is actually 0. So your flight path angle would be 0 in these three cases, and so that will be a really useful tip for you guys as you go forward trying to calculate these things. All right, so let's talk about our launch site velocity. So the fact that our launch site is fixed on a rotating Earth. So here we've got a rotating Earth, and it's going to be spinning counterclockwise. If you remember, it's turning 15 degrees per hour. And so if our launch site, depending on whether it's near the equator or if it's closer up here to the poles, it's going to have a particular velocity. And that velocity is actually going to increase as we move away from our axis of rotation here. So on the equator, we're going to actually get a little bit more boost of our launch site, and that's going to be related to this equation here that V launch site is equal to 0.4651 times the cosine of our launch site latitude in the east direction. Since the Earth is rotating east, eastward, our velocity of the launch site is always going to be eastward as well. Next, we need to figure out what the velocity we require to overcome gravity. So that's going to be V loss gravity. To do that, you can manipulate the fact that we've got a specific mechanical energy initially and a specific mechanical energy at final position. So initially we might be at the surface of the Earth, or we will be, and finally we're going to be up in our actual orbit. So that would be at RBO. You can set up your specific mechanical energy equation here and realize that at our final velocity, we're actually going to be, we can assume that our velocity is going to be 0 here. And then we can manipulate this equation algebraically to solve for our V loss gravity as this expression here. And this is going to be in the zenith direction. So this is the velocity that we're going to need to just overcome gravity. We can put all of these things together in our launch velocity equation, which you see here represented in matrix form, where our delta V needed is expressed in the S, E, Z components. And here we have our VBO terms, and this is the amount of velocity we need to achieve the orbital velocity. And this is this next term here is the velocity from Earth's rotation. So notice there's a minus sign here. So this is a part of our velocity that we don't have to take into account. So this is something that the Earth is going to give us for free. So yay Earth. And then lastly, we have this V losses, or lost gravity rather, which is in the Z direction. So this is how much velocity we need to achieve orbital altitude. So we put all those things together and we can calculate our delta V design. So we're going to work through some more problems in class, but hopefully with the slides that you've seen or with this video, you'll know how to calculate, or you'll know what the launch vehicle ascent phases are, what the topocentric horizon frame is, also known as the SEZ, and you should be able to do some cursory calculations of your delta V design. Thanks. We'll see you next time.
I am back to you now to talk about launch velocities. And of course I got my trusty ancient TI-86 here, and we've got the wonderful equation sheet such as it is with all of its beefy, juicy info. And I have last year's as I have my homework problem from last year. So let's begin. I'm going to show you how to do this problem, and it's going to take you less time than coronavirus spreads, and that's pretty fast. Hey-o. All right, just kidding. But you got to laugh through this stuff a little bit. Okie dokie. Let's begin. Okay, so as always, we give you some starting conditions, right? A satellite will be launched from the following launch site in a perigee of the given orbit. That actually is a big deal. We'll talk about that in a second. The launch site is 28.5 degrees north, longitude 80 west, which you guys are starting to hopefully recognize. You're like, oh, that's Cape Canaveral, right? That's Kennedy Space Center. It's just a side note, and it makes sense that we use this lat long for a lot of our launch problems, because that's where we launch a ton of our stuff from. And okay, it says local sidereal time is 0200. So it's kind of in the middle of the night, early morning. And our parking orbit, which is the orbit we're going to, launch our spacecraft into, has a semi-major axis of 8500. So pretty low Earth orbit. Slightly eccentric, right? 0.1 there, and then an inclination of 40 in a RAN of 90. Great. So first things first is assuming the launch azimuth for the next launch opportunity is 44.5 degrees. So you guys remember from the last lesson where we actually had to nug out what the launch azimuth was. Well, they're just kind of giving it to us here because the point is not necessarily to nug all the way through that. They say, okay, so if you guys remember the launch azimuth, the Greek letter for that was beta. That's not the best beta ever written, but yeah. B with a long tail, right? Greek things sometimes have long tail. The letters do. It says, answer the following questions. What is the flight path angle at burnout? Okay, so this could in real life be a lot of things. But what I'm going to show you and what I'm going to tell you is phi. So that's my best way of writing phi, is a circle with kind of a line through it. I don't know how to write the Greek. It's this letter, in Microsoft Word, but phi, right? That's what that is. That's how you say it, how you write it. It's going to be 0 degrees. As a side note, put your calculator in degrees for this. Because remember, the only two things you really do in radians are orbit prediction and rendezvous, because those equations are specifically built for radians. They don't do very well when you try to use degrees. So you can leave your calculator in degrees for this problem too. All right, flight path angle at burnout. Well, what's the flight path angle? So let's see. For a circular orbit, or even let's see. You know what? Let me take that back. Let me use the example of an elliptical orbit like we're actually doing here. Highly exaggerated, of course, right? That's not what 0.1 eccentricity would look like, but it says we're launching into perigee. But this would be true also if we were, launching into apogee. I'm just going to let you assume that's apogee. Worst apogee ever drawn. And now it's recorded forever. Cool. So that distance is going to be position vector, or position magnitude at perigee, position magnitude at apogee, right? Problem says we're launching into perigee, but the point is flight path angle is going to be 0 in this class. That phi, that flight path angle, is always going to be 0. I've seen homeworks in GRs where we do tell you that. I've seen homeworks in GRs where we don't tell you that. I would recommend go ahead and commit that to memory. Let that be one of the penguins on your mental island, that this flight path angle for Astro 310, it's going to be 0 degrees. Because we are launching into perigee or apogee. Well, you might say, well, what if you give me a problem where I launch into apogee, where I don't launch into perigee or apogee? And I would tell you, don't waste any mental penguins on that, because for this class, it's a little beyond the scope of what we're trying to do. So, okay. B, what's the velocity at burnout? So I will tell you on this, also, it's not specifically on your equation sheet. It's vaguely on your equation sheet. So let me write it a certain way and see if you recognize it. You might remember that the velocity of a satellite in an elliptical orbit is this classic. We only use the classics here. What if I told you that because we have an elliptical orbit and we're launching into perigee, we have to use that velocity equation because we're in an elliptical orbit. We're launching into an elliptical orbit. Ta-da! Okay, so what this really turns out to be when you do a little substitution, the velocity at burnout needs to be, basically, let's assume that we only put enough fuel in our rocket to get to where we needed to launch. What I mean is, once we launch into perigee, like it says we're supposed to do, to perigee of our parking orbit, we're out of gas. Let's assume there's not a single drop left in that booster, or a single fuel grain if it's a solid rocket, but no fuel left. So velocity at burnout is basically just going to be the velocity at perigee of that orbit. So what you end up with here, substituting in a few things here, mu over r burn out minus mu over 2a. Remember that this is negative mu over 2a. Now, the question is going to be, what a do we use here? I think you might be able to agree with me. That is the center major axis of our orbit. No. Now, what position magnitude are we using? What radius, if you will? R sub burnout. So if we're burning out, basically if we're out of gas when we finally launch in and we finally get to perigee of our parking orbit, like we didn't put any extra fuel in, we've burned out at perigee, then that means this is just radius at perigee, which is a times 1 minus e. Of course, you guys remember that's direct from your equation sheet. So now, as always, the most pleasurable part, plugging and chugging, here we go. I'm just going to put that in there. 1 minus 0.1. Okay. So minus, I need more. 98600 over 2 times 85. 100, let's see what we get from that. I should not be negligent. Let me put the 0.5s on there like I should. Divided by 8,500 times point minus okay, and multiply that by 2, and we take the square root of the square answer. That makes sense. 7.5 kilometers per second or so. That is very typical for Leo, as we note. Okay, circled, done. All right, now what takes a little more calculation is this delta V needed at burnout. So I am looking right here. Delta V needed, we break up in the equation sheet into the 3 vectors, right? South, east, and zenith pointing. So that is your topographic horizon coordinate system, right? Yay, we get another coordinate system for launch. And it's focused, which makes actually a lot of sense. It's focused at the launch site. So, zenith is directly up. That's what the direction that the rocket is launching. And then south makes sense and east makes sense. Those are cardinal directions. We can make sense of those, at least in some way. So basically here, what I'm going to do is a little housekeeping before I even plug in anything. So delta V needed in the south direction. I'm just going to kind of draw a little line under, that's the south component. So it's this negative VBO, cosine phi, cosine beta. Okay, great. Delta V needed east is in between those, right? It's going to be this VBO, I say VBO, velocity of body odor. No, of course. V sub burnout. So when we write RBO or VBO, that's what we're talking about, our radius of burnout or velocity of burnout, times cosine of phi, sine of beta, that launch azimuth, minus the velocity of the launch site. So there's a couple things that I want to do that are housekeeping: the velocity of the launch site and the velocity of loss due to gravity. So let me take those before we plug anything in. I'm going to section myself off a little space up here to do velocity of a launch site. I'm going to abbreviate that V sub LS. And it equals 0.4651 cosine up. L sub naught is back. Oh, how odd. The velocity of the launch site, you might say, is, well, I'm not on the shifting seas of the ocean, and my launch site is not on top of a NASCAR that's moving at 150 miles an hour, so why does my launch site have any velocity? And I would say to you, well, it's not relative to you standing on the Earth. It would be relative to, for example, you might, if you were an observer standing on the sun with your sun boots, because you need sun boots, otherwise it would be too hot. Anyway, if you're an observer on the sun, you'd look out at the Earth and say, oh, not only is that planet going around this giant ball of fire, it's also rotating on its own axis, right? So by virtue of the fact that the Earth rotates on its own axis relative to an external observer, your velocity of your launch site has some actual velocity. And it's based on the latitude of that launch site, right? The north-southness of the launch site. Well, we're told that 28.5 degrees north is our launch site latitude. So let's plug and chug. Okay? Cosine of 28.5. Kind of counterintuitive and weird, but if we launch east at all, our vehicle rather gets some added velocity, which is really handy. So the velocity of the launch site is 0.49. I'll go ahead and truncate that, kilometers per second. Now, that's good. But I need to do V of losses due to gravity. So what is this? Well, when my spacecraft is thrusting upward, the only reason it really has to invest almost any energy at all is because there's gravity, right? That's what we're fighting when we pack that rocket, that booster, full of very combustible materials and then point that combustion in a certain direction. It's to fight gravity so that we can actually get our spacecraft into orbit. So losses due to gravity is something that is non-negligible, right? It's significant. So let me do this little part up here. So velocity V of velocity lost due to gravity, right? So, or put another way, how much faster would we be going if the Earth had no gravity? So V of losses due to gravity is 2 mu. Oh, 2 mu. R sub BO minus launch site over RBO times radius of launch site. Cool. This is a really quick plug and chug. Let's get free points together. Free points on the GR are good points. That's all I'm saying. Okay, radius of burnout we found. Let's see. Actually, we found it up here, although I just kind of plugged it and chugged it. Let's see. I didn't solve it on its own. Mm-hmm. 7650 minus radius at the launch site. Okay, this is tricky a little bit. We make some assumptions about the radius of the Earth, right? 6378. You guys are so used to type it in your calculator, your fingers are tired of it by now, right? 6378.137 kilometers. Well, okay, that's a pretty fair average. Like if you're an alien in Andromeda and you had a great telescope and you could see Earth, you'd say, oh, that's got about a radius of 6378. But obviously you all know it's not true. The difference between the top of the Himalayas and sea level is significant. So what we're assuming here is we're launching from Cape Canaveral. That is basically sea level. It's right on the coast. So we're just going to assume that because the launch site is right on the coast there, we're launching at the radius of the Earth, which is to say 6378 kilometers from the center of the Earth. The only exception to this might be if you were launching from an aircraft, which sounds weird, but there's a couple of companies that have, there was a company that had a 747 that they would fly, and it would have hanging off of one wing or under the underbelly of the aircraft, I can't remember, but hanging off was a booster. And basically that jet would get up as high as it could get, and then it would allow the booster to launch from the aircraft. And so basically in that case, instead of launching from sea level, you'd launch at radius of the Earth plus whatever height of the aircraft it was. And those launches were not quite as common. They were launching smaller spacecraft into orbit. But that is a story for another time. Just be conscious of where you're told you're launching from. You're not told that you're launching from an aircraft. We would be very explicit about that. If not even giving you a picture, we would tell you in as many words. So what I mean to say in all this is radius of the launch site, it's just the radius of the Earth in our problem. Okay, radius of burnout, 7650. Radius of the launch site, 6378. Okay. You know what I'm going to say. Let's plug and chug. Wait, 2 times. Okay, so I get about 1.5 kilometers a second. And that checks. That squares with kind of what we know. All right, so now we've got our velocity of the launch site and our velocity of losses due to gravity, again, which is basically like saying how fast could we accelerate to if there were no gravity, right? What portion of the booster is going to just fighting gravity of the Earth? So it's about 1.4 kilometers per second worth of booster fuel. Now it's time for the ultimate plug and chug. And I say ultimate because we're going to do it in this kind of monster vector format. Delta V needed south. Delta V needed east. And Delta V needed, zenith. And we're going to keep these in line. You'll see what I mean in a second. Okay. So negative V BO times cosine phi cosine beta VBO cosine phi sine beta. Oh, tricky. VBO sine phi minus quantity 0, velocity of launch site 0, plus quantity 0, 0, V sub LG. Okay. Equals. All right. Now let's plug and chug. We are not scared. We are not intimidated. This is no biggie. 7.57 cosine 0 cosine. Let's see here. We are given the launch azimuth, which is nice. 44.5 degrees. 7.57 cosine. Why did I write cosine phi when I just know it's 0? Sometimes I have a habit of writing 0 like that, and that's an old habit. But okay, anyway, cosine 0 sine 44.5. 7.57 sine 0. Ooh. You know what? I'm just going to combine them all in the same bracket, which you can do. You can do it. So minus 0 plus 0 minus velocity of the launch site, which we found was 0.409. And this is minus 0. Minus 0 plus 1.442, because that's the velocity of the loss due to gravity. Let's see what this comes out to be. Alrighty. Times cosine of 0, which is 1, times cosine of 44.5 minus 0 plus 0, so that's easy. All right, that ends up being negative 5.399 kilometers per second in the S direction, which means north, right? Negative south means north. And then, that was deep, right? Let's see, times sine of, and cosine 0, sine 4.5, negative 0.409, or minus 1. Okay, that means 4.97 in the east direction. And then, of course, 7.57 sine 0, that just goes to 0. So that just ends up being 1.442 S hat, E hat, Z hat, kilometers per second. And this is us circling our answer here. Okay, cool. Now, the last bit. Assume velocity of losses other than gravity, which is just to say, we lose some velocity due to imperfections just in the world that we live in. So we're going to give you this value, V of losses other than gravity. Our equation sheet says the delta V design that we want, and this is the holy grail kind of this whole math problem here, is the absolute value of, we're going to have to do absolute value again, magnitude, here it comes, delta V needed, which we just found. We found it in vector notation, which is good, plus V losses OTG, I call it, other than gravity, OTG. Well, you guys remember how to do magnitudes. It's the square root of negative 5.399 squared plus 4.897 squared plus 1.442 squared. And then that whole thing plus our velocity of losses OTG, which they just gave us here. So if we plug and chug, I wonder what we will find. Alrighty, so that ends up being 7.43. It's 1.1, and of course that's going to give us 8.53 kilometers per second. We're going to have to stuff our rocket full of enough fuel so that we can get a little more than 8.5 kilometers per second worth of boost out of it. And that'll overcome kind of the imperfections in the world that we live in, right? VL, OTG, it'll overcome gravity. Thankfully, we get a boost from our launch site. Anyway, it takes all those things into account. And now you guys can literally say that you are rocket scientists. Oh, there's my thumbs up. Thumbs up. Rocket science. Okay. It's been fun as always. We'll see you guys next time. All right, you guys, it's Major Cunningham again. It's Major Cunningham who made a mistake. I made a mistake on the launch velocities video, and I wanted to make this quick addendum, this quick correction. So everything is good to go all the way down as far as part C, where for the velocity that we lose due to gravity, I fat-fingered in the radius of burnout, or sorry, the radius of the launch site. Apologies. So I'm going to real quick go through this again, and I have already checked that this answer is much closer to correct. So let's see, 7650 minus 6378, 1137, boom. Let's see, boom, divided by 60 times 68, 1137. That's where I made the mistake last time, take square root of that. And instead of getting 1 something like we did before, I actually get 4.559 kilometers per second. So everything again else is good except for the velocity delta V needed in the Z direction, right, in the Z hat direction. So that's down here. So this will get basically plugged in right here, 4.559 kilometers per second. So that will mean that it's actually 4.559 kilometers per second down there in the bottom, because we have the S component is fine, the E component is fine, the Z component not fine. And so then again we're taking the magnitude of the delta V needed, where we would take the square of the S direction, the square of the E direction, the square of the Z direction, take the square root of all that. Well, all that was okay, but I need to plug in 4.559 down here. So now let's see what that gives us. Partial credit for me, right? Maybe. Boom. Square root of the square answer. 8.59 plus 1.1. So this ended up being 8.597 plus 1.1. That gives me not 8 something, but instead 9 something. That's what I get out of that, and that should be good to go. Thanks again for listening along, guys, and thank you to the cadet, who I would love to know whose name to give them thanks, but thank you for identifying this group to me. I review these videos before I post them, and I totally missed that, so I will review more closely. All right, thanks, guys. Bye.